Section 15.3 is on conservative vector fields and independence of path. Our objectives are to understand and use the fundamental theorem of line integrals and understand the concept of independence of path. In a gravitational field, the work done by gravity on an object moving between 2 points in the field is independent of the path taken by the object. In this section, you will study an important generalization of this result. It is called the fundamental theorem of line integrals. In this example, we want to find the work done by the force field, f of xy, the vector field, equals 1/2 xyi plus 1/4 x squared j. Now this represents a field of vectors, and those fields of vectors can be seen represented with these little short vectors in the plane. Now we want to look at the work, find the work done on a particle that moves from the point 0, 0 to the point 1, 1 along each path. In the first path, we're going in a straight path from the point 0, 0 to the point 1, 1 along the equation y equals x. In part B, we're looking at this path here, x is equal to y squared. We're moving from the same beginning and end point, but we're moving along a different curved path using the equation x equals y squared. And in part C, we want to find the work done again, same beginning point, same ending point, moving in the same vector field, but we're using the path y equals x cubed. So we'll go through and work through each one of these, calculating the work done, and then we'll talk about what it means to calculate the work in a conservative vector field. Okay, let's begin with the first path along the straight line y equals x. We need to come up with a parametrization for the path. And if we're moving along this equation here, y is equal to x, we can begin by letting x equal t, and then it follows that y would also equal t. So our parametrization, our r of t, our path, can be represented as your xi plus yj. In terms of t, we can represent it as ti plus tj. And we do need a time interval here. It would, beginning with t equals 0 and ending at t equals 1, that would give us the correct start and end point. So the time interval here is for t goes from 0 to 1. When we calculate the work is a line integral of f dot dr. This dr is calculated by taking the derivative of this path we just found, this r prime of t. So let's calculate that r prime of t will equal the derivative here. We're going to take the derivative of t to get 1i plus the derivative of t here to get 1j. Again, the same time interval here. Now we can begin to write our definite integral for work. So it's going to be an interval from a to b. The a to b is found by this parametrization, the time from the start to the end. So that's going to be from 0 to 1. And we need to write this vector field f in terms of t. We are going to write every x in this with what it equals on the path, and every y in the vector field with what it equals on the path. So we can begin that substitution and replacing x with t and replacing y with t as well. That's your I plus the 1/4, and I'm going to replace the x here with t squared j. So what I've done is I've written the vector field in terms of t by itself. Now we want to find the dot product of that vector field with r prime of t, and we've already calculated that down here to be 1i plus 1j, and then all of that is dt. Now you should have only the variable t in this definite integral, no x's or y's. We've made the substitutions to eliminate those variables. Now let's simplify this. This becomes a definite integral from 0 to 1 of 1/2 t squared I plus 1/4 t squared j dot with the 1I plus 1j. Now remember um, when you find the dot product, you multiply the corresponding components and then you add the results. So we're going to get the integral from 0 to 1 of 1/2 t squared plus, when we multiply 1/4 t cubed times 1, we get 1/4 t, I'm sorry, that should be squared, not cubed. Looks like it times our dt. Now if we simplify this, let's kind of move that out of the way here. If we simplify this, we get the definite integral from 0 to 1, 1/2 t squared plus 1/4 t squared. When we simplify those, we get 3/4 t squared dt. Okay, now you can evaluate this definite integral, and you get the work calculated by the force field on an object moving from the point 0, 0 to the point 1, 1 along this straight path is equal to 1/4. That's our final answer. Okay, for the next example, we're going to switch the path. Same vector field, same start, same end point, but the path is going to be different. Okay, in this case, we're moving along the path x equals y squared. We need to come up with a parametrization for this path. That's a little bigger. Okay, you can begin by letting x equal t, but if you let x equals t, then y would have to equal, if you solve for t, y is equal to the square root of x, so that would be the square root of t. But I don't want to get into finding the derivatives of that, so there's got to be a simpler way to do this. We can begin by letting y equal t. If you let y equal t, then x would have to equal t squared. It's just we'll save you just a little bit of work there by making that parametrization. When you do these parametrizations, it's not unique. There's an infinite number of ways you can come up with this path. So with practice, just choose one that may tend to simplify the calculation. So if this is our parametrization, then our path is going to equal r of t is your xi plus yj. So this is going to be t squared I plus tj. And we need to figure out the time interval from the start to the end. If we choose that time interval from t equals 0 to t equals 1, then we can verify that it is going to start and end at the desired locations. When we calculate the line integral for work, we do need to find the derivative of this parametrization for path. So we can go ahead and find r prime of t. That's going to be 2ti plus 1j, taking the derivative of each of those components. Now let's go ahead and write our line integral for work. The line integral is f dot dr, and this is found by taking the vector field, the force field, and replacing any x with what it equals on the path and y with what it equals on the path. So it's going to be 1/2. I'm going to replace that x with t squared, and I'm going to replace that y with t, and that's your I, plus 1/4. Again, I'm replacing that x squared, replacing that x with t squared, j. Okay, so that's your entire f vector written in terms of t. We're going to dot that with your r prime of t going down to here, which we found to be 2ti plus 1j, and then that's your dt. One more thing we want to point out here is the time interval. The bounds of integration correspond to the time interval, so this is going to be an interval from 0 to 1. Let's simplify this. Line integral for work, it's going to be an integral from 0 to 1. Then we get 1/2 of t to the third I plus 1/4 t to the fourth j. We're going to dot that with 2ti plus 1j dt. this we can simplify by doing the dot product. The 1/2 t cubed times a 2t is going to be t to the 4th power plus 1/4 t to the 4th times 1 is 1/4 t to the 4th. All of that dt. If we add those together, those like terms, we get the line integral is, for work, is a definite integral from 0 to 1 of 5/4 t to the 4th dt. Okay, evaluate that by taking the antiderivative and substituting the balance to simplify, and we find that the work done on this object moving from 0, 0 to 1, 1 in that vector field along that path ends up being 1/4. Okay. Now, if you recall, that ends up being the same result that we got in the previous example. Now, that doesn't always happen, but let's see along that last path. Okay, here again we are moving in from the same start and end point. The field is the same. The only difference here is the path. So let's come up with the parametrization for the path. Let's let x equal t, and let y equals t to the 3rd power. That would follow here. So our parametrization, or r of t, that path here is ti plus t cubed j. The time interval here would also be from 0 to 1. Our path, when we find r prime of t, the derivative of that is going to be 1I plus 3t squared j. I'm going to switch up the notation here just to show you that you can use the ij notation or you can use the angle bracket notation. And what this is going to look like is the interval from 0 to 1 using the angle bracket notation here instead. I want to write 1/2 of xy. I got to replace x and y. We're replacing x with t and y with t cubed. Again, I'm just using that parametrization I came up with. And then the j would be 1/4 x squared. Got to replace the x with t. And I want to dot that with your r prime of t. If I write this using the angle bracket notation, it's 1 3t squared dt. I actually tend to like this notation better since I'm not writing as much, eliminating the i's and the j's. So this now becomes, when we simplify it, the definite integral from 0 to 1 of 1/2 t to the 4th, 1/4 t squared. I'm going to dot that with the vector 1 3t squared dt. Let's simplify that. Okay, we get the integral from 0 to 1. We're going to multiply the corresponding components together to get 1/2 t to the 4th plus 3/4 t to the 4th dt. Again, writing that as a single definite integral, combining like terms, we're going to get 5/4 t to the 4th dt. And when you evaluate that definite integral, you also get 1/4. Okay. Again, if you go back to the previous examples, the answer was the same in this case. The work done on all these 3 different paths was the same. Let's go back here. Again, when we calculated the work for on the straight path, the work was equal to 1/4. When we calculated the work on the second path, the work was also equal to 1/4. And when we calculated the work on that third curved path, the work was also equal to 1/4. In this case, the path actually did not make a difference for these 3 examples. This doesn't always happen, but it does happen in certain cases.